Hello, in this video we're going to step things up with our analysis of moments of inertia and working these out. And we're going to look at a shell. So this is a hollowed out sphere which is rotating about, well in this case I'm going to put a vertical axis of rotation in. So essentially I'm going to draw this sphere is quite small because I'm going to zoom in on what's quite a tricky diagram to draw on this. So we've got this shell, it's spherical shell. It's just rotating horizontally about this vertical axis of rotation. We can say that the shell has got a mass of capital M and a radius of capital R. Now, the reason this is a lot more difficult is we've moved into 3 dimensions here. So when we're using our, if you remember our moment of inertia formula, we're wanting to add up, a bit of a wonky sigma sign there. So we're wanting to add up all of our points that we're going to create over the surface of this shell, and we want to have the mass of each one of those little bits of the surface multiplied by the radius, or the distance squared from the axis of rotation. So this is the thing that we're wanting to fill in. Now if I zoom in on a little bit of this, and what I'm zooming in on is, yes, we think we've got some little bit of the surface here of the shell. So exactly how are we going to work out what the mass and the radius of this is, sort of generically, so we can then add them all up over an integral. So let's zoom in on this little bit of the outside of the shell. So we're going to have something that's all looking a bit curved, a bit like this. So say that's zoomed in there. Right, this dimension here is, if we trace this back, we can trace it back to, it's a little bit wonky with my picture here, but this is tracing back to the very center of the whole of the shell. So that's drawing in here, that little bit, that slice going into the center, and it's going to be coming down to a point at the origin. And it's a distance r from the center because we're measuring from the center out to the surface of the sphere. So we know this is r on both sides. And we've got some little bit of angle here. So we need to throw in some measure of angle. So let's say we've got an angle that we're measuring from the center of the sphere, where straight up along the axis of rotation, that's 0. And then we're measuring this angle theta coming down, and then we've got a little bit of theta there. We've got a d theta. So we only want a little bit because we want a small bit of the area. We're trying to get a dA in here. What little bit of area have we got for the total surface? So we've got a d theta. So this gives us the extent of one of our dimensions here on this area, that using our knowledge of circles, we've got r d theta. Now, the other dimension, I'll switch over to red, we can do a similar thing. So let's think of this going round. So say this was then extending all the way round into a horizontal circle. Then that's giving us the other dimension to this area. And we can trace that side back to, so this is all lying on the axis of rotation that's going through the center of this shell. But we've got another angle now. This time we've got an angle which is being measured in a horizontal plane. So we call that an angle phi, so we don't get it mixed up with theta. The distance away from the axis of rotation is not capital R, because capital R has to be measured from the center of the sphere. So we call this little r because that little r is exactly the same as the little r that we've got in our moment of inertia formula. So we've got a little r there, and we've got a little bit of phi. So we've got a d phi. So this dimension of this area is an r d phi. So we've got a capital R d theta and a little r d phi, and that's giving us our area. So we can now say that dA is going to be equal to r d phi times r d theta with a lowercase r and a capital case r, uppercase r. And that's going to be fine, because when you get to the limit, you know, we're going to be turning this sum into an integral, or in this case, it's going to be a double integral, because we need to integrate over theta and phi. We've got two things that are varying here. Now, as we go into the limit, these curved lines, because this RD theta and the RD phi, they're actually curves because they're on the surface. But that's going to go in the limit down to being the same as a little rectangle. So we can just multiply those and say we don't have to worry about it being curved anymore. We can say, yeah, that's what the area is. Right, now we need our dm, dm, I'm going to put that in inverted commas. So the little bit of the mass of the total shell, and the reason I'm putting that in inverted commas is that's this mi, really. That's our dm that we're going to be adding up. So that is going to be the mass of the entire shell times the fraction of the shell that we've got. And that is dA divided by the total area of the shell. So the area of a shell is the surface area of a sphere, 4 pi r squared. So that's our mi. That is mi. And we've got our dA. What else can we say about this? We've got lowercase r and we've got an uppercase r, and we don't want this little r sitting around really, because we're integrating over phi and theta. So r is varying. Capital R we know is a constant, so that's fine. We can leave that in our integral. But this lowercase r is varying with theta. You can see as theta increases from 0, as we're sweeping out this angle here, lowercase r is getting bigger. So r is a function of theta. So we need to make sure that's in our integral. But we can see, looking at the geometry, all of this, that sine theta, so opposite over hypotenuse, is r, little r over big R. So we can bring that in as well. So now we just have to put all of this together into one big double integral. So we've got I is going to be the integral. So for phi, that's going to be, we're going from 0 to 2 pi. For theta, we're going from 0 to pi, because we only have to go from the top down to the bottom. We're not coming back up the other side again. We're not going all the way round in theta. Once we've reached down to the bottom, we've covered everything, because the phi going all the way round, every time we take a step down, we're doing the entire sort of ring of points for every theta. So yeah, we don't have to go down and back up again, otherwise we'll be double counting. So that's covered what we're integrating over. So what have we got now of all of these bits that we're putting in? So our mi is m over 4 pi capital R squared. Then we got dA, so that's r, then a capital R, d phi and a d theta. So that's our dm bit. And then, but we also need an r squared thrown in there as well, which is going to be capital R squared sine squared theta. So we need to tidy up all of this before we start doing our integral. So let's cancel a few things. We also need to get rid of this r here, because we don't want this lowercase r in there. So we're going to have to put another r sine theta in there using this relationship. So let's get rid of that, and then we can put in another r, so make that a squared, and we'll make that a cubed. Right, now we can cancel a few things. So that r squared will cancel with that r squared. And now we're not looking that bad. We can start pulling our constants onto the outside. So we've got an m, we've got an r squared, we've got a 4 pi, and I think that's everything, isn't it? Yeah, and then we've got our double integral. I'll leave the limits off. We can see what those are from the one I've written above. And then we've got a sine cubed theta and a d phi and a d theta. Now, one thing that I'd mentioned from the start of all this is I'm taking the fairly long-winded approach. One thing that you'll see when people do this in textbooks is they can say, well, each time we've taken a step down in d theta, we're just getting another ring here. And we've already worked out in a previous, much simpler video, the moment of inertia of a ring about an axis going through the center. Um, so, and because moment inertias are just adding things up, we can integrate moments of inertia in order to get another moment of inertia. So if we added up all of the moment of inertias of all the rings that make up this surface, we would get the moment of inertia for the new surface. And you can see that in this. That if you think back to the video that we did when we worked out the moment of inertia of a ring, we were doing an integral from 0 to 2 pi of what was it, m over 2 pi, but it was just oh, and we had an r squared as well in there, and we were just integrating. Well, in that case, we called it d theta. So that is, you can see this is sitting inside, is actually this first integral that we're doing here, which is now just the d phi bit. That is actually working out the moment of inertia of this ring, everything that's in the phi direction. It's working out that ring, and then we're doing a second integral, which is adding up all of the moments of inertia for all of those separate rings. I've just done this, I've gone all the way back to the beginning. So rather than saying, oh yeah, we've already done this bit, I'm just going all the way from the start on this surface of the sphere. But if you were starting from that point, then that's fine. Right, so where have we got to? So we've now got to do this double integral. Well, the only thing here is fine with doing the phi integral, because all we're going to do, there's nothing here varying with phi, so we're just going to be getting a multiple of 2 pi on this. So that is that moment of inertia of a ring. So we can now get rid of that first integral and the d phi, because we've just done it, and multiply everything by 2 pi. So we've got mr squared over 2, and now we've got the integral from 0 to pi of sine cubed theta d theta. Now that integral is easier said than done. We're going to have to do a substitution on this. So if we say, first of all, we want to, let's flip over color on this. We're going to want to rewrite this. This is one of these ones that once you've seen it, you know how to do it, but it's quite hard to just come up with it on your own. So we can rewrite sine cubed theta as this. As I've changed the sine squared in it into a 1 minus cos squared. So we've got sine theta times 1 minus cos squared theta. We can then say, well, let's let u equal cos theta, so that du is equal to minus sine theta d theta. And now we can stick all of that in to our new integral. So this is now leaving us, the outside hasn't changed, we've got mr squared over 2. We need to change our limits because we're now going to be integrating with respect to u rather than theta. So cos of 0 is 1, cos of pi is minus 1. So we're going from 1 to minus 1 now rather than 0 to pi. We're then changing what we've got inside the integral. So we've got a sine theta d theta is going to be a minus du. And then we've got 1 minus u squared times minus du. So we're going to have u squared minus 1 times du, just flipping the sign. So that's just plugging all of these bits here into this integral in order to now integrate over u. And this is now straightforward, isn't it? Because we've got mr squared over 2, u cubed over 3 minus u between those limits. So what's going on inside this when we put the limits into our definite integral, we're going to have well, we've got minus 1, oh, minus a third, plus 1, then we're going to have minus another third, and plus another 1. All right, so we've got 2 minus 2 thirds, so 1 over 1 1/3, 4/3. So all in all, we've got 4/3 times mr² over 2. So that's 2/3 mr², and that's our final answer that we've got on all of that. So this is a lot more involved. So I don't really see many people having a run through all of this. And don't worry if you find it particularly confusing, because it's you don't really need to do all this very much. It's worth running through it though a few times, just to see that you're getting used to this idea that we're integrating twice. Make sure you understand the picture. That's probably the main thing out of all of this, that you can understand that we've got one measure of angle which is going down vertically, from top to bottom. We've got another measure of angle which is going horizontally. And those two things combined are giving us our two variables in this integral that we need in order to work it out. And that's why we've got these two integrals going on here. So it is a particularly complicated one. But yeah, run through it a few times, and also then look at the one, we're going to have a similar problem when we do this with spheres, like a solid sphere rather than just the shell. But the approach is pretty much the same, really. When we're looking at the solid sphere. But yeah, there you go. It's worth trying these things and stretching yourself a little bit. Yeah, but it's not easy.